Hello, everyone. My name is David. I'm working under Emmanuel de la Torre in Emmanuel de la Torre's group, and this work was done in collaboration with Matan Bendov and under the supervision of Emmanuel de la Torre. And we're going to talk about optimal strategies of characterization of crosstalk in quantum computers. So, what even is crosstalk? Well, crosstalk is a side effect of coupling between qubits. This coupling is what enables 2-qubit gates, but it's important to understand that the crosstalk as a side effect will not go away as the hardware will get better, because, as I said, this coupling is essential. So this coupling actually creates coherent errors. And here is like the simplest example I could think of. This was an experiment that I ran on an IBM quantum computer. The experiment was this. I initialized a qubit in the plus state. The blue line, the blue experiment, there was only a single qubit. The neighboring qubit was at 0, and I let it evolve in time. As you can see, the fidelity of the qubit went down, but not as fast. The red experiment, I did the same experiment again, but this time the neighboring qubit was initialized to the 1 state. And as you can see, the fidelity to the plus state went down extremely, much faster. So to explain this phenomena, let's look at like the simplest model we can think of. The Hamiltonian will be like that. First of all, we'll have the self-energies of each qubit in the system. We'll call it the detuning, omega. And we'll have the crosstalk terms, the coupling effect. What you'll see is that, firstly, the detuning is basically the energy difference between the 0 and 1 state, or the detuning from decalibration. And the crosstalk effect, what it will do, it will cause a level splitting in the 1 state. Imagine if we have 2 qubits, if one qubit is at the 1 state and the neighboring qubit is also at the 1 state, then the energy difference would be omega plus j instead of simply omega. So, so this crosstalk basically acts as an effective detuning at when the neighboring qubit is on. So to look at crosstalk, we'll first try to characterize detuning and see how we can go from there. So to characterize this detuning, we'll look at something called the Ramped interference experiment. This experiment is fairly simple. We start at the 0 state and apply a Hadamard gate on the qubit. This will transform the qubit to the plus state, the superposition of 0 and 1. We'll then let it evolve, and we'll see that the 1 state will acquire phase with respect to omega. And then we'll measure at the x basis. And the expectation value of x would be a simple cosine omega t. Now, to complicate matters a bit more, we'll add T2 dephasing. So in addition to the self-energy of the qubit, we will add a random field H. This random field, the mean value of H would be 0, and the variance would be gamma over 2. The effect of this T2 dephasing would be that, for example, if we start the plus state, the expectation value of x and y would decay exponentially. So now, how do we actually estimate those parameters? How do we estimate omega and gamma? So if the expectation value is this cosine, this decaying cosine, we can never actually measure this cosine. We can only perform measurements and get 1 or minus 1. And we can always perform only a finite amount of measurements. So we always have an error in our expectation value that we calculate. So, and this error will go as a 1 over square root of n. So what we'll do is we'll take our measurements, we'll put them on a graph as a function of time, and those measurements, again, they will have errors. They will deviate from the true function. And we'll try to find a function that minimizes the distance between it and our measurement data. And well, hopefully what we'll find is the correct cosine omega t to some degree of error. Now, this method, this is what we'll call the first method, is actually the industry standard. Like, this is what Qiskit shows on their documentation, and this is how we usually find the detuning and the dephasing rate. So now, is this the best approach that we can think of? Are all data points created equally? Or another way to ask this question is, should we measure at many times with a low amount of accuracy, or few times with high amount of accuracy? Because remember, we have a finite amount of measurements, and the question is, how do we actually divide those measurements? To answer this question, we'll look at something called the likelihood function, the Fisher information. The likelihood function is simply the probability to obtain a data point under a specific parameter theta. Now, another way to think about it is how well our statistical model explains our data. This is a function of theta, right? The x is, like, theta is the variable. And the Fisher information matrix tells us how much information our data carries about a parameter. And it is defined as the average over the second derivative of the log likelihood function. This means that if in our likelihood function we see a narrow peak, a small insert, this means we have a high amount of information. And if we have a flat peak and it changes slowly, it means we have a low amount of information. So again, is there a limit to the precision? And the answer is yes. And this limit is called the Kramer-Rao bound. And this bound tells us that the variance of an estimator is always larger or equal to the inverse of the Fisher information matrix. And an estimator is simply a black box that gets as an input our measurement data and outputs a guess about the parameter. So what we need to do is simply find an experiment that carries the highest amount of information. So that's what we'll do. We'll look at the inverse of the Fisher information. And our theta, the parameters, would be the omega and gamma, the detuning and dephasing, will be the measurement times and the number of shots per measurement. Now, omega and gamma is something that we can't change. What we can change is the measurement times, t, and the amount of shots per measurement time. So we'll assume that for now that we can only measure on the x basis, and we'll simply run this optimization process, like find the minimal value of this function. And what we'll see is that if we assume many measurement points, we will see that they all converge only into 2 measurement times. And so the first strategy, or the second strategy, would be calculate those 2 measurement times, T1 and T2, and measure on the x basis those measurements, those 2 points, will fit to our data and extract the parameters omega and gamma. For example, for omega equals gamma equals 1, the 2 times would be T1 equals 0.44 and T2 would be equal 1.78. If we have access also to the y basis, we'll only need 1 measurement time. And interestingly, this measurement time would only depend on gamma. The measurement time would be simply 1 over gamma. And again, we'll measure on both x and y and fit our data to those functions only at a single point. So to convince you that this actually works and this is better, we'll compare those 3 methods. The 3 methods would be, the blue one is the equally spaced. This is what Qiskit tells us to do. The second one, the green function, the green line would be measuring at a single point, a single measurement time on the x and y basis, and the red one would be measured twice only on the x-axis. And what we'll see is this. Again, we're comparing the 3 methods, and we'll also compare something called the Kramer-Rao bound. The Kramer-Rao bound should be the optimal bound. This is what was calculated for the green method. What I'm showing here is the tuning frequency error as a function of the number of shots. This is a log-log graph, and what we can see is that all measurement strategies, the error goes as 1 over square root of n. But while the difference might be small here, it is clear that the green method is always better than the red and then better than the blue. But there is a fundamental flaw in this strategy. And the flaw is that to calculate the measurement times, we need to know the parameters in advance. So what if we don't know the parameters in advance? Like, this is what we need those strategies for. So to explore this question, what we did is we calculated the optimal measurement times for omega equals gamma equals 1, and then ran the simulation with different parameters of gamma. So what we can see here is that as we increase gamma, obviously the error rate, the error in estimation will go up because we are deviating from the optimal parameters. But the green method, basically measuring in both x and y axis on a single measurement time, is much more stable. It goes up much more slowly. What I also show here is that the dots are actual. This is from a simulation. This is the error that was calculated from a simulation, and the lines are the Kramer-Rao bound that correspond to this method. And we see that they actually follow this trend. It actually sits nicely on the graph. So now we return to crosstalk. How do we use this to calculate crosstalk? So we'll start by calculating the tuning for all the system. We'll partition our circuit or our qubits into odd and even qubits, assuming we are on a chain. We'll do this basically to neutralize the effect of crosstalk. So each qubit will acquire phase only as its own energy omega. After obtaining omega, we'll partition the system again in a way that each qubit has only at most one neighboring qubit that is active at a time. And this time, what we'll see is that it will acquire a phase as omega plus j. And we can treat it as just as an effective detuning. This is like the exact same experiment. And now what we can see is that here, instead of choosing a specific parameter, we sample the parameters from a ordinal distribution. And what you can see that, again, the green is better than this time than the blue, that is better than the red. But still, the measuring at x, y at a single time is much, much better than measuring at x, only on the x basis. And another thing that we can see on this graph is that the error does not depend on the number of qubits. Like this can scale infinitely because we measure all the qubits simultaneously. So again, if the number of experiments is a valuable resource, you should optimize the process and calculate the Fisher information and find the optimal measurement times. So right now we're working in collaboration with another research group in the Bar-Ilan University and with IQCC to test this experimentally, and the work will soon be published about that. Thank you very much.
So usually when you calculate the Fisher information, you have to specify what is the classical Fisher information. You already have the set of data that you have.
Okay.
Quantum Fisher information, you have to first also optimize over the observable that you're measuring. And here you're using two non-commuting observables. So how can I assign a probability distribution function for two non-commuting observables? So what is the Fisher information you're comparing to?
Okay, but here the Fisher information is completely classical because the probability distribution is simply a Gaussian around the mean value that we're measuring. Like, we know what the expectation value should be, and we know what is the probability distribution to measure, like to get a measurement around this expectation value.
But it's a probability distribution function of what? Of x or of y? Because they're non-commute, so it's a problem.
We first measure for x and y, right? Like we know that. Oh, sorry. I think I pressed the wrong button. That you told me not to press. Just a second. So, like here, for example, you see that x is equal to cosine omega t, and so the probability distribution would be a Gaussian with the mean value of cosinus omega t, and standard deviation that is dependent on the number of measurements that will go as 1 over square root of n.
So imagine x, right? X is the thing we are calculating efficient.
Yeah, x or x and y simultaneously. Like not simultaneously, but yes. Yeah. Every time I measure, like I get a simple bit, right? 1 or minus 1. To get an expectation value, I need to measure many, many times or a different experiment.
Right, but there's no joint probability distribution function for x and y, I think, right? In quantum mechanics.
That is like a sum.
You're not in the single experiment measuring x and y. There are one experiment which you measure x, you go home, you come back the next day, you measure y.
Yeah, but what's the Fisher function you're calculating?
So the Fisher function is like the sum of the Fisher function for one experiment and the
Yeah, exactly.
It's a sum of both of them.
Yeah, it's exactly. Yeah.
So if you have both x and y at the same time, essentially you know where you are on the Bloch sphere.
Exactly.
So you can actually calculate, you know, analytically, surely if you assume it's just decoherent, you can get gamma right away, right?
Like I need to do it in an experiment. Like this is what I'm doing.
Well, yes, but you don't have to optimize the time for this. In each time you do it, you will get immediately this relation. Just x squared plus y squared will give you the radius, and you get the decay from this. It's not something you need to fit, no?
I'm not sure I agree with you because it will depend, like where I am on the Bloch sphere will depend on both on omega and on gamma. But okay, I know, I understand what you're saying. Yes, exactly. And this is exactly why measuring on y is much more stable, and this is why measuring on both x and y depends only on the here. Oh, here, only on 1 over gamma, because like you can imagine it as like the x and y as a like a complex like graph, and it's like the time evolution would be like a spiral that decays. So yeah, exactly. To measure gamma, the dephasing rate is the radius of the single point, and omega is where I am at the like at what angle I am.